Alright, let's change it up a little bit. How about sums of cubes? Sums of cubes look something like this. It's almost the same as the difference of cubes, except that this is the sum here, and that these two things are the only things that are different. And you could do this, I'll let you think about it. You could use the kindergarten method. You would set it up like this: x squared plus negative xy plus y squared, and then you'd have x plus y here, and then you would multiply. And you'd see what you get. You'd get x to the third plus y to the third. So this becomes something famous, something that you should be comfortable recognizing and using at any time. It comes up a lot, so that's why we're spending some time doing it. Again, abstractly, these things could be anything, and you get, as long as this is plus and that's minus, the number of triangles decrease, the number of squares increase, and you have a triangle and a square out here, then that's the perfect pattern to recognize as this. Okay. Same thing with 2, so it doesn't matter. So this is the plus, this is the minus, the number of 2x's decreases, the number of 1's increase, and you have the 2x and the 1 out here. So it must be 2x to the third plus 1 to the third by sum of cubes. Okay? Alright, let's switch it up a little bit now. So now we go classic here with some Greek stuff. This guy was a Greek mathematician, Pascal. Made a name for himself with some nice stuff. And today we're going to use some of his ideas to be able to multiply things like this. X plus y to the 0. Well, you'll see this turns out to be easy, but what if it's to the 1 or to the 2 or to the 3 or to the 4 or to the 5? Don't confuse that with these ones. These ones are different, where you have x to the 4 plus y to the 4. That's the sum of fourth powers. That's not what we're talking about. We're talking about when you just have the sum of two items and then you have the exponent outside. That's the key. The exponent is outside. These ones are called Pascal polynomials. So let's do the first one. The first one's going to be rather easy. When you take almost any number to the 0, if I take 5 to the 0, it's equal to 1. If I take 7 to the 0, it's equal to 1. For almost any number to the 0, it could be anything, I get 1. The only exceptions, there are some exceptions. 0 to the 0, we don't know what, that's called an indeterminate form. You have to pay a lot more money to figure that one out. Other exceptions are things like infinity to the 0. You have to pay more money for that one. But if these are non-zero real numbers, anything to the 0 is equal to 1. So assuming that x and y, when you add them, don't give you anything like 0 or infinity, if they give you a plain old regular number, a real number, then that would be equal to 1. And that's the end of it. That one was super easy. How about that one? Well, what does that mean? 1 mean on the right hand side? That 1 on the right hand side means that you write this one time. And so there, by definition of natural exponent. Well, that one was super easy. Wow. How about for the square? Well, that, now we're getting somewhere. The 2 means write it twice. X plus y. That's the definition of natural exponents. That exponent means write it twice and multiply it. Then I could use FOIL, so that would give me x squared plus xy plus yx plus y squared, and that's by FOIL. And then I could combine like terms, an x and a y and an x. I could use commutativity to commute these, and they're like terms. So that would give you x squared plus 2 of these, 2xy's plus y squared. And of course, that would give you the famous PP number 2. It's not bad, right? PP number 2. And so you just have to recognize that every time you have to square something, you can distribute the, if you have a plus here, if you have a binomial, you can distribute the 2 to that exponent, distribute it to that one, but don't forget there's a middle term that comes from the FOIL. Okay? That's the lesson to be learned here. And then you go on to the third. Well, the third means the same thing as x plus y squared times x plus y. That gives you a total of 3. That's the by natural exponents. Actually, this is by just adding the exponents. Just adding the exponents. 2 plus 1 is 3. And of course this one we already did. This is x squared plus 2xy plus y squared times x plus y. And that's PP2. That's the one we just did a couple minutes ago. And so now you have a trinomial times a binomial. Luckily, we've done this stuff before because we have the famous and powerful kindergarten method. So you could do this x squared plus 2xy plus y squared times x plus y. And see how it fares out. This will be y to the third. This will be 2xy squared. If this is too fast for you, You can just slow it down, pause it, and do it yourself. X squared y. If it's too slow for you, you can fast forward it. Play it at double speed. That's the beauty of videos. X to the third, and so I get that this is x to the third plus 3 of these, 3x squared y's plus 3xy to the third. I have an xy to the third, and I have 2 more xy, sorry, xy squared and 2 more xy squares, a total of 3xy squares. Plus a y to the third, and now we're good. This right here is super famous. This is Pascal polynomial number 3. Look at the pattern here, look at the pattern. How many x's do you find here? 3 x's, 2 x's, 1 x, no x's. It has the same pattern as the difference of squares or difference of cubes. The number of x's decreases, the number of y's increases. No y, 1 y, 2 y's, and 3 y's. The only thing that's different here are the coefficients. For the difference of cubes, all the coefficients here were 1. For the Pascal, they're not 1. They got these other numbers going on here. And so the goal is now, can we do x plus y to the fourth? And now it's time to see why it's called Pascal. Watch this beautiful stuff. So you make this triangle that's called Pascal triangle, and the idea to make the triangle is you start off with 3 ones, and then you add whatever's above it, whatever 2 items are above it, or if there's only 1 item, you add whatever's above it, and you create the next row. So here I have 1 and a 1, I add them and I get 2. Here there's only 1 thing above, so I have a 1 and a 1. Here I have 1 plus 2, that gives me 3, 2 plus 1, that gives me 3, and a 1. Here I have a 4, here I have a 6, here I have a 4, and here I only have 1 thing, so it's a 1. And so on and so forth. Here I only have a 1, here I have a 5, here I have a 10, here I have a 10, here I have a 5, and here I have just a 1. And so this is famous, this is called Pascal triangle. The reason it's famous, among other things, it tells you the coefficients of these expansions. Let's take a look at here what happened. X plus y to the 0 we said was equal to 1. X plus y to the 1 we said was equal to x plus y. X plus y to the second we said was x squared plus 2xy plus y squared. X plus y to the third we said was 1 plus, x to the third, 3x squared y plus 3xy squared plus 1y to the third. Now you start to see the pattern here. This is a 1, that's a 1. This is a, I'll change colors now, watch this. Let's go with, I'm gonna go with, shoot, tough choices, 1. So this is a 1, and this is a 1 and a 1. Notice that 1 and that 1 there. This is a 1, a 2, and a 1. That's the 1, the 2, and the 1. Now you see how the pattern matches up. This is a 1, a 3, and a 1. And that row right there has a 1, a 3, and a 1. That's where we get the coefficients from. That being said, we could easily multiply x plus y to the fourth. We would just first understand the pattern for the variables. They decrease, so you have x to the fourth, x to the third, x squared, and then an x. They go down. The y's on the other hand go up. No y, 1y, 2 y's, 3 y's, and 4 y's. And the coefficients you get from here, from this row, from the fourth row, or the row that has a 4. So this would become, let's do it in red again to be consistent. This would become 1 x to the fourth, 4 x squared, x cubed y, 6 of these, 4 of these, and 1 of those. And that, my friends, that's how you do Pascal's triangle. Okay? One more, just for fun. That was so fun. We're going to do it again. This time we'll go in yellow here. Yellow, x plus y to the 5th power. Alright, first we understand the pattern. You got 5 x's, 4 x's, 3 x's, 2 x's, 1 x, and no x's. Now the y's. 1 y, 2 y's, 3 y's, 4 y's, 5 y's. So my x's are decreasing, my y's are increasing in numbers of them. I know you can barely see that. Alright, now the coefficients. The coefficients I'm going to get from my Pascal triangle. So the coefficients will be a 1, a 5, a 10, another 10, another 5, and a 1. And I put pluses in between everything. And that right there is Pascal triangle. PP polynomials. Probably the most famous one is this one, PP number 2. We will be using this one over and over and over again. This is what we will use to complete the square and eventually solve all degree 2 equations in the real world. This is one of the most famous ones, PP2. But you should know all of them, and that's how the whole story fits together. All right, I think we're doing good here. We should focus on. Oh yeah, again, don't confuse that with this. This is not Pascal. Pascal has to have the exponent outside. Then it's Pascal, not where the stuff is inside. Okay, I think that's good for today. We did some famous stuff, some timeless polynomials. You guys will get a chance to practice those on the flashcards. We'll see you guys here next time. Peace.